So I prepared the set of slides, and I think I have a few things that I think I want to clarify and I think you should know. Other than that, this is not the right talk. This is not the right title for the talk, but it is the right talk. Other than that, I really think you can ask me the things that you would like to know, and we can make it more of a sort of interactive discussion rather than a talk. So let me remind you, we're talking about a proposal that proposes for all of the LSST Cadence, which means for the wide, fast, deep, which is the main survey, which will cover at least 18,000 square degrees, with a cadence that is sort of semi-regular over the 10 years of the survey. How regular remains to be defined, with all of the filters, as well as the mini surveys. Those are special pointings, sets of the sky that you will cover with a different cadence. Generally, those are multiple pointings, so you want to think about a mini survey as a collection of LSST pointing coordinates. And the deep drilling fields, think of them as a single pointing for LSST. They're intended to be fields that will be explored more in depth, so with higher coadded stacks, higher magnitude limit, as well as with higher cadence, if that is what the community needs, to detect transients at certain specific cadences or characterize the light curves better. A lot of the details really need to be defined, but it would be unusual to propose for a deep drilling field that is either not deep or not drilling, or doesn't have a high cadence. But really kind of everything is possible. So think about the deep drilling fields as single pointings, whereas the mini surveys are collections of pointings, larger areas of the sky. As well as for special programs like the Targets of Opportunity, which may or may not be enabled for LSST. It's likely to be considered very seriously for gravitational waves, as well as twilight survey and surveys that happen, which means surveys that happen in the time that is not really constrained by the total amount of time that we know LSST will have over the 10-year surveys minus the wide, fast, deep. So the way the survey will be organized, there is a certain amount of sky hours in 10 years that are in dark time, and the wide, fast, deep will take a fraction of that. Which will range likely between 80 and 90%, depending on the details of how the wide, fast, deep is run, to cover the 18,000 square degrees or so of the sky that will enable the science cases of dark energy, dark matter, and as well as the study of the transient sky outside of special regions. The rest will be a competitive process between the mini surveys, the targets of opportunity, and the deep drilling fields. There are technical constraints. I went over them yesterday, but just to point them out one more time, the technical constraints come from the scientific requirements of covering the 4 science cases: dark energy and dark matter, the study of the galaxy through the resolved stellar population, exploring the transient sky, and cataloging the solar system. Particularly the dark energy and dark matter requirement establishes the size of the footprint of the wide, fast, deep survey, which means how large is the sky that the wide, fast, deep survey will have to cover, and it's set to about 18,000 square degrees. There are a few simulations that cover a larger area of sky with a wide, fast, deep cadence, but this is sort of understood that it should be the minimum. There are constraints on proper motion that require a certain cadence for the visits. Those constraints end up being rather weak, but the visits are distributed throughout the lifetime of the survey and throughout a season in a way that enables this parallax and proper motion constraints, at least in the R band. And there is a requirement of rapid revisit, which I want to bring up again. So a certain fraction of the sky, a smaller fraction of the sky, about 2,000 square degrees, is required to be revisited at a shorter time scale, between 40 seconds and 30 minutes. Scientifically, the justification for this is that there aren't really very many surveys that do this such rapid time domain science, so there is a space for discovering of the unknown. So there could be transients that we're not aware of that work on those timescales in those depths. And in practice, it's enabled by running fields that overlap. So if you imagine, for example, a survey that selects the fields along the meridian going up, and then turns around and goes down along the meridian again, that survey can be implemented so that images that are on the same latitude will overlap partially, and this gives you the 2,000 square degrees of overlap out of the wide, fast, deep survey. Okay. We propose for the white papers through this white paper proposal call with deadline in November. And again, you can propose for any of these surveys. And specifically, there are some things that the project has pointed out that I would like to hear about in the proposals. If you're proposing for a wide, fast, deep survey, you want to mention what is the sky coverage of a wide, fast, deep survey. For example, does the wide, fast, deep survey extend to the galactic plane? What is the filter depth for every filter? If you're proposing for deep drilling fields, you can propose additional pointings. There are 4 selected pointings. Even the pointing for those selected pointings can be modified, so it's not been optimized. Those pointings were selected earlier, and they will be imaged because since the selection, they gather collateral data, so they gather data in other wavelengths and with other surveys that will be useful to do science in those fields. But more fields are possible, and again, you can still play around with the exact pointings within those fields' footprints. And the detailed cadence strategy for the deep drilling fields is completely open. So with the selection of filters, the total depth of the deep drilling fields, and the cadence, what is the time interval, the time gap between images, this is completely open, including in the 4 deep drilling fields that have been proposed. And then a number of mini-surveys that the project has mentioned were talked about or proposed in the past include the galactic plane as a mini-survey. You can also conceive of the galactic plane as a part of wide, fast, deep. North ecliptic spur, south celestial pole, but any other pointings, there is a collection of pointings, say large and small Magellanic clouds, is fair game, as well as modifications and proposals for specific cadences on these 3. When you think about the cadence, you should specify the optimal visit exposure time, the other per band pass image depth, the sky coverage, the temporal coverage. All of those things should be discussed, even if it's to the extent of saying, all I care about this mini-survey or the implementation of the Wi-Fi sleep that I want is the sky coverage, and I don't really care about the temporal coverage. That still should be mentioned. Let's go into a little bit more detail. There is a submission template, and actually it's rather informative. It has sections that you should fill in, and they're described. So that's the very best starting point to understand what you should include in the paper is the submission template. I'll go over it in a second. And here are the information on how to submit the paper, since this is, I think it's the title of this talk. You will email the paper simply to this email address. There's no portal for submission, but also there is a community-specific portal for asking questions about submission and about the white papers in general. So again, the timeline, the November 30 deadline. What happens after the November 30 deadline? So if we understand that, that will help us, I guess, understand how to write the paper. So the people that will make evaluations on these white papers, which by the way, shall strictly not be called proposals, because they're not proposals, they're white papers that don't get accepted or rejected like a proposal would. Rather, they get ranked. The Science Advisory Committee will read the papers and will rank them in the sense of ranking the priority to simulate the survey strategy that has been requested in that paper. So with this ranked list, which will appear in April 2019, the project and the Science Advisory Committee can design multiple options for the cadences. Notice this is important. It doesn't mean once the cadence is ranked even highly, it doesn't mean it will be implemented exactly the way that it was written in the paper. But actual designs will be based on the white paper submissions. And the reason for that is that it is very likely that cadences will be merged between papers. Similar cadences will be merged into a single cadence that is useful for more than one science case. Once these designs appear, then the project will go on to simulate the op scenes. So they simulate each one of these strategies that have been designed. Each one, I should say, up until they have manpower and computational resources to do that, down that list. And then, together with the simulation comes the implementation of the metric analysis framework. So not only the project simulates the strategy, but also they run a set of maps, a set of metrics that measure the performance of the op scene, of the simulation for given goals that may be scientific. For example, they may run metrics like supernova discovery. They may run the existing metric that says how many supernovae are detected given this survey, or they may be technical. They count the number of filter changes that the survey requires, things like that. And just to continue on, a single strategy will be closed to begin the project, and then regular survey reviews will continue to happen throughout the life of the project to evaluate the strategy success, possibly modify it and improve it, but also to reevaluate scientific priorities in the light of potential discoveries. So far, so good? Okay. The evaluation criteria for the papers are written out as the science important and legacy value of the proposal. So this point was made earlier about what does this mean in terms of a proposal that is incremental versus a proposal that is revolutionary, maybe high risk and high reward. And it is important to point out that in the paper proposal call, the project has spelled out that one of the criteria is whether or not this proposal scientifically matches the unique capability of LSST. So it takes advantage of the large field of view, of the large entendu, of the depth. And it's something that another telescope could not do, could not compete on doing. This will be a criterion for evaluation. And then whether it's consistent with the four main science goals. The feasibility, and there's indications on how to look at whether your proposal is feasible as you design it, and I'll go over them in a second, and the time requested, which means if two wide fast deeps are proposed and they achieve similar scientific goals, the one that is most efficient, so this relates also to the efficiency, most efficient and it requests less time, should be used so that more mini surveys and deep drilling fields can be enabled. Okay. The proposal has three main sections, really four, but let me go over these three that are more obvious. The scientific motivation section, so you want to explain your science case. This will be important if we talk about merging science cases, and I will tell you what my recommendations are about that at the end. But either way, you should include the scientific motivation, the technical description of the section, and this should be in enough detail that if you can write a math, it will go with it. So if you can write an evaluation of the survey, based on your scientific proposal, that should go with it. The code should be accessible to the project and the SAC. But if it's not, this section should have enough detail that the project itself can go simulate, can go create a math to run it on all the op scenes. So you should specify what are your observational requirements in terms of number of visits or co-added depth or whatever you need, types of filters, filter gaps, so that those things can be embedded into a Python code that can be run against all of the maps. And then the performance evaluation section, which should be carried out. So if you don't have the metrics for your science, if you don't have a clear idea of what your science design, it may be actually hard to go over this section. The performance evaluation section can be written based on existing metrics, but you have to understand very clearly what your observational requirements are. Okay. In more detail, the technical description has about an infinite number of subsections. I'm going to just briefly mention what they should contain. Obviously, a high-level description of your survey, just these many these many observations in these filters with those time gaps, etc. And then the footprint and pointing, which I was discussing with somebody earlier, it may not be clear what this is. What regions of the sky do you need to observe with that cadence? If you're asking for a cadence that is great for blazars, you really want that cadence to be applied in extragalactic regions. And if you are jointly asking for a proposal that also includes the galactic plane, then that becomes extragalactic and galactic. If you really only care about the bulge and you're designing the survey specifically to address the bulge, then you should make clear that the footprint of that survey is contained to the bulge. The image quality requirements, most of the other subsections can be addressed with existing metrics. So you need to get familiar with math, even just to understand which ones of these metrics you can use on the existing opsims or on opsims that you create, if you create any. Yes? Do you remember? Yes, I have the templates here. I don't remember the number of pages, but I have. Yeah. Some of the sections are not constrained. The scientific motivation is 2 pages plus 1 page for figures. The technical description, this is interesting because it is actually not constrained and it's sort of the longest one. And I don't know the answer to that. And the other sections are ranged between 1 and 2 pages. There's 5 sections, so I will actually pester the project a little bit more to know how long they expect the technical section to be. The image quality, for example, the image quality can be expressed as maximum air mass or darkness, how dark the fields are. So you can run those metrics that already exist on the existing opsims and say this opsim, which is similar to the one that I want, performs as such in terms of image quality. I need my performance to be better in this area. Okay? The individual image depth and sky brightness, it's just metrics for all of these. I'm just going to show you that the metrics basically, when you write a math and you run it against opsim, a set of default plots are created. For example, this is a median metric, so you create a metric that says what is the sigma depth per image in this opsim. You choose a band, this is the U band, and you take the median, you take a statistics over there, you take the median of those. And these plots are created as a default. This is a map, a color map of the median sigma depth, and this is a histogram, so this is the number of fields that will have that sigma depth, and so is this. Notice that this was the individual sigma depth, which may change for different strategy. Well, obviously change if you change the exposure time total, but it may also change depending on how you distribute the images in the sky, whether you're asking for dark time for a mini survey, that would affect how the wide fast deep sigma depth ends up coming out, and the co-added image depth per visit, or the total number of visits, similar things. And I plotted 2 of these because I think it's interesting to see how there are already simulations that have quite different requirements. Let me think about which ones these are. This is the Kraken, which is the baseline. It's sort of the one that complies to the sort of back of the envelope description of LSST, 18,000 square degrees, 4 deep drilling fields, etc. And this is the Postus, one of the Postus simulations that is extending the wide fast deep to the entire sky. So this simulation doesn't have the North ecliptic spur and the galactic plane as a separate streak because it's implementing a single cadence on the entire southern hemisphere as well as far as wide fast deep goes. So basically the idea here is these are no longer mini surveys, they're just part of the large survey. And you can see that the difference is quite dramatic you can't see anything because you see no resolution, but this is the co-added 5 sigma depth. Okay. The number of visits within an eye, this can also change very much. For example, it would change a lot if your survey is a deep drilling field versus the wide, fast, deep. Also metrics for assessing that without having to write them. Distribution of visits over time. The filter choices in your survey. This is important. Perhaps if your science only benefits from G, R, and I, and you're asking for a mini survey, that can make a significant difference. But even if you're asking for a wide, fast, deep implementation on a specific area of the sky, say the galactic plane or the bulge, perhaps you don't want U-band, and you probably don't want very red filters. You may not want them, and so it is important to state that because that affects the overall time, efficiency in time of the survey. Exposure constraints, do you actually need 215 seconds exposure, 130-second exposure, other constraints, etc. This is a really handy table that they ask you to fill in the paper template to rank basically the things that I discussed before, but in some more detail: image quality, sky brightness, individual image depth, etc. Rank how important these things are for your science case, for the survey that you're proposing. This is very similar to the infinite, what was the name of the one paper, Angela, infinite diversity and infinite, something or other. This spreadsheet that collects not necessarily white papers, but science cases and ideas of what they need and how they could be implemented, which is going to be in addition to the white paper. So that's not going to be submitted as white paper, but it's going to be possibly supporting them and even exploring things that didn't make it into a white paper because people didn't make it to write them. And was one of the products from the Flatiron Institute meeting. Yeah, sure. Roadmap, yeah.
Actually, we already sent our contribution. What's about the score?
Right.
I have to say that some people are still confused about the different things. I mean, that roadmap is for obligation.
Right. So roadmap, really, we have some urgency in getting a roadmap in place because that helps publications. It helps mostly funding, looking for funding. So going out to the right foundation and pitching the right thing, which is something that we won't do ourselves, but mostly Jana Sokolowski, who will do it on our behalf, and if she has a roadmap, she can do it more thoroughly and more insightfully. It's a very different thing than the white paper, the white papers that will actually influence the strategic decisions of LSST. But there's overlap, right? Because once you know your science case, once you know what kind of science you want to do and what kind of observations you need for doing that, which should be in the roadmap, then you can use that into the white paper and add to that a MAF and an OPSIM request. The last two sections are performance evaluation and special data processing. The special data processing, let me start with that. If your images are unusual, say you want a shorter exposure time, or you want to do very crowded fields, then the pipeline that Colin just described may not produce the results that you need, may not produce the data that you need, may not be sufficient for deblending those regions, or may be unable to provide the intra image, like the snap photometry that you need. Then you need to create data processing pipelines for that, for your science. And it should be clear in the paper whether your science can be done with the standard pipeline products, or it needs what used to be called data, level 3 data products, and it's now called user-generated data products. And both how difficult they are, how different they are from the pipeline, which will basically state how difficult they're going to be to create, as well as if you have a plan for doing that, as well as what is the computational requirement of those. Because I would imagine that most of the people that want to write user-generated, that want to run user-generated pipeline will want to run them on the LSST platform, so they don't have to export 30 terabytes of data per night, especially if they're time-sensitive data products. And so the project needs to know that these spatial data processing pipelines won't violate simply the amount of resources they have, the constraints on the amount of resources that they have available for users. Just a couple more things. So the software, relates to that statement. The project will not create non-standard pipelines to process the data in a non-standard way, and requires the special processing is planned in both in terms of resources and in terms of algorithm, or at least that there is an understanding that there is a plan and a possibility of producing it. So some of the open questions on a survey-by-survey basis for the wide fast deep, for example, there is a trade-off between sky coverage and number of visits that should be explored. So in your paper, you should state whether you're intending your wide fast deep your wide fast deep should be broader or deeper. The time allocation per band remains to be defined. There is an idea of running a rolling cadence as opposed to a wide fast deep, a traditional wide fast deep cadence. So what this means is the wide fast deep cadence, as it was described earlier, is intended to be the same cadence for the 10 years of the survey. So you would have the same, basically the same alternation of fields and the same gap between observations of the same field for 10 years. This is not great for transient science because it ends up having gaps in time between same filter in excess of 15 days, which basically means if you're interested in supernova, you really cannot do supernova science with the wide fast deep. An alternative would be to focus on an area, front-load an area of the sky, and so focus on that with shorter time gaps in the early years of the survey, and then move to different, focus onto different regions, while lowering the number of visits, the density of the visits for that region. This is generally called the rolling cadence, and various rolling cadence implementations are being explored. If you're interested in transient science, this should be something that you really should think about, making sure that the rolling cadences that are being proposed make sense for your science. AGN is generally opposed to running a rolling cadence, or particularly to running a very aggressive rolling cadence. Supernova type people would rather have a rolling cadence, so there is a bit of tension here. Yeah. Yeah, no, please.
Is in that case, let's say if we want to monitor variable stars during all the 10 years of
Right.
and we can choose to use a rolling cadence, let's say for the first month of every year, first week of every year, something like that. The proposal should be a wide fast deep proposal. It's not the main
Yeah. The rolling cadence is an implementation of the wide fast deep. But I don't know.
Should we declare this in the wide?
Oh, yeah. Yeah. Whether your survey, your wide fast deep is homogeneous in time or it's rolling, yeah, you definitely should make it clear.
Should we define that?
Yes.
Is for
Here when it says white paper information, this is asking you, is this a mini survey? Is this a wide fast deep or a deep drilling field?
and in that case, it's required.
This would be a wide fast deep with rolling cadence. But again, I just want to make sure that the idea of the rolling cadence is clear. Because of the proper motion constraints particularly, you will always cover all of the sky every year, basically. But you could imagine if that wasn't in place, that constraint wasn't in place, that LSST would do only like 1/10 of the sky in the first year, 1/10 of the sky in the second year, etc. Again, that's not going to happen, but that would be the most aggressive rolling cadence. And so a less aggressive rolling cadence would be, for example, spending 10% more time on one field, on 1/10 of the sky on the first year, and the rest on the rest, and then moving that 10% of the sky. Again, if you're interested in very long-term variability, you might have a constraint on homogeneity. And so you want to spell that out, and you want to spell out that in your science, that your science case will be affected by an aggressive rolling cadence. Let me mention this last thing. So the snaps, again, I said that a couple of times, but I think it's important for a lot of the people here. Right now and until now, nearly all the simulations have been done with two snaps that combine form an image, and those snaps have been 15 seconds each to form a 30 seconds exposure, which is what gets analyzed by the prompt data product pipeline. And this is now being questioned, and it's being questioned in a number of ways, but particularly there is a fairly compelling argument to move to a single exposure, which is 30 seconds long as opposed to two 15 seconds exposures, because that removes essentially the readout time of the first image, while the readout time of the second image can be done during slew time, so it's really much more efficient, and it gives you back 7% of the time. Consider that we're talking about having 10 to 20% of the time available outside of wide fast deep, and compare that with the 7%. This is a compelling argument. Again, if you're worried about saturation, or if you're interested in very short time scales, intra 30 seconds time scales, you would lose that, and you will be affected by this. And this actually, I put it in the wide fast deep open questions, because that's how it's spelled in the proposal call. But this actually affects all of the science, all of the surveys. If you want to propose a mini survey, you should spell out, I really want it to be 15 seconds as opposed to 30 seconds, etc. These are the four deep drilling fields. These pointings are set, but not in detail. The dithering on these pointings is not defined. The cadence on this is not defined. The filter set is not defined, other than the fact that these pointings generally will be in the field. Nothing else is defined about these four deep drilling fields. It's not defined how many deep drilling fields will be done. So if you want to propose for a survey strategy that needs 8 deep drilling fields, you can. It will all be limited by how much time is available. And then mini surveys that have been proposed just for historical context and that should still be reproposed. So other than those 4 pointings, everything else, even if it has been proposed in the past, it needs to be reproposed, or the older proposals, like the proposals from 2011, will not be considered competitive with the current proposals. So the galactic plane survey, there have been a proposal for a galactic plane survey. I mentioned yesterday there will be a few. There's also an extension of the wide fast deep proposal that extends to the galactic plane. The Southern Celestial Pole has been talked about and generally is included in the observations as a mini survey. Maybe it's not necessary. It's absolutely not clear what cadence or depth it should be observed at. The Northern Ecliptic Spur, obviously the solar system team really would like to see these, but it's not clear how far north you will go or what the cadence should be, and if any other science will benefit from it, such that the cadence should be tuned to sciences other than the solar system. And then twilight surveys, which brings me to the last thing I'm going to mention. So there are some requirements for evaluating the performance of the cadence. And here are information that you can use to do that, and sort of scaling laws for the various things that you're proposing. So there is a minimum of 3 seconds slew time. So when you consider proposing a survey strategy, if you have a very specific way of designing the way in which the sky will be covered, because I don't know, because you really need a wide area within a night, keep in mind the slew time, and keep in mind the overhead that slewing significantly would put on the survey. And this should be stated if your survey has requirements of going all over the sky every night. This should be stated in your paper. There are currently 5 filters at any point in time on the system. There exist 6 filters, so you can observe in 6 filters, but only 5 within a night. This is because of the geometry of the filter wheel that cannot host 6 filters, it can only host 5. So the filters get swapped once every, I don't remember, but it's written somewhere here, and basically replacing Z or Y with U during dark time, because who wants to observe in U during non-dark time? Otherwise, you can use all the other filters. You can exchange filters fairly rapidly, but there is a limit to the number of filter changes that you want per night. 90 seconds plus 30 seconds, this seems too long, Colin. Is this wrong? 120 seconds to change a filter? 2 minutes?
You have to de-rotate the camera.
Oh, okay. Okay, well then consider that 120 minutes of that time if you want a filter change. There is a maximum load over the lifetime of the telescope, so think about that when you design the deep drilling fields. And a maximum number of filter changes over the lifetime of the system. And there are efficiency constraints that generally scale with a number of things. So if your OPSIM is phrased in terms of exposure time, or if it's phrased in terms of co-added depth, you can basically scale the efficiency of the survey based on the current surveys whose efficiency has been evaluated with these set of equations. You don't really have to do all this, but you have to look at this to understand that your request has enough information so that somebody else can go and do that, so that the project can go and do that. So the last thing, you need to create a figure of merit and a metric for the paper. The figure of merit and the metric are the things that we discussed earlier. You don't really need to create it in terms of coding it up in Python. This will be what we saw Owen doing in the video. It's not true that every white paper needs to have its own metric that is coded up in Python so that it can be run on the simulations. But what is true is that you have to have a figure of merit. So, and the way that these are, that what a figure of merit is phrased in the COSEP in the paper that, in the Philip Marshall paper, I have a link to that here, observing science-driven optimization of the observing strategy. Is very clear, and I recommend that you read the introduction to that paper to understand it. But basically, because LSST is trying to do a whole bunch of different sciences together, and in that it's a survey like no other, those different science goals and those different science topics have to be compared. So they need to be in the same units. So we need a single number, not we. The SAC and the project need a single number to evaluate how well a particular science goal is performed by a strategy. So that I can compare it to how well a particular science goal is performed by another strategy. And then, of course, there will be some weighting of this science goal based on the overall scientific importance, which is, I agree, somewhat subjective, but somebody's going to have to make the decision, so that will have to be considered. But I think that our responsibility as we propose these things is to make a science case and give an evaluation of how well a set of observations can perform on that science case. So this is the figure of merit. For example, it's clear if your target is cosmology, a figure of merit for cosmology can be the predicted dark energy W0 minus WA. Generally, things like that, those kind of fields have a single quantity that they're trying to measure. So it is somewhat clear how to create a figure, of merit for that than to say, for example, my favorite example, which is one of my science fields, understanding the progenitors of supernovae. I don't know on a scale from 0 to 1. I mean, there's no real way to answer that question. It's a complex, loaded question. But it is our responsibility to come up with an answer to that question. There is a single number so that supernova progenitors can be compared to cosmology. For example, it could be the predicted number of transients that are classified correctly, or the inverse of the Fisher matrix determinant, anything like that. The diagnostic metric is what the math does. It takes an OPSIM, and based on what the figure of merit is, it asks questions about the data that is returned by OPSIM. Number of observations per filter, or maybe filter gap. The power spectrum density function parameters, the sigma depth, the intranight gap, things like that. Those things should be in the paper. These set of things are rather easy to code if you just look at a couple of coded maths, and there may be small variations on existing coded math. If you don't feel like coding it or you can't get to coding it, or you don't know how to code it, that's fine, but it has to be described in words so that Lynn Jones and Peter Jochen can go and code it once the paper has been ranked. So that then every paper can be used, can be evaluated. Every science case can be evaluated for all the options that are produced. As general recommendation, and this gets to be rather my personal my personal feelings of how I think a competitive proposal would look like, but I don't really have any insight because I'm not on the SAC that will evaluate these papers, so I can't, I don't know, and they don't know yet how that process will go in detail. But I think you should obviously prioritize clarity in both the description of what you need and the description of what your science case is. Understand synergy and tensions and spell them out in the paper so that we know that if your observing strategy is great for blazars, but it's also good for supernovae, that's a plus. And then earlier I was asked how about gathering support from the scientific community to emphasize how important the science case inherently is. That is a brilliant idea, especially if your science case is one of those that have been less talked about in the context of LSST, for example, if it's galactic plane as opposed to cosmology and dark energy and dark matter and weak lensing. Keep in mind that fragmenting the reason why in these plots TVS looks like it's dominating and is because we are planning to present many papers. So there is a necessity here because we're planning to request many different surveys. But if you can gather a science collaboration and make a single proposal, that stands to be a stronger proposal. So if you can join papers and if you can unify your voice, there may be an advantage there. I would think about it as a survey-centric process. So I would try to merge the science cases that benefit from the same survey strategy. And this is really important. You need to stay together with the figure of merit and that metric. You need to state what the tolerance is. So you can design your ideal survey that says, I need 17 observations in 2 filters every night on the same field. But if everybody designs an individual dreamlike survey, we can't converge on a single LSST cadence. So together with that, you also have to state, but also my science case will be okay as long as I have 3 observations per night in 2 filters, or whatever your science case is. So understand the limits at which point you're unable to perform your science, and also give tolerance around your request. 3 observations per night plus or minus 1 makes a much stronger case than just 3 observations per night. I think that was the last slide that I have. I have a bunch of links here, so when I give out the slides, you can click on any of these places where you can find resources for understanding metrics, math, etc., and people that you can actually contact to ask questions.
Any question or comment?
So about the figure of merit. So now it's clear that you have to quantify but you have, I suppose, to normalize as well, because if you want to compare different figure of merit, you have a similar normalization. So the idea that you have to have a value 1 when it's your perfect survey, 0 when nothing, and you have to find an algorithm, normalization function that in some way, for example, if I count the number of transient, which can go, I could be 1,000 as I had then divided for this function.
Exactly, so it works really well if you think of number of things, and so that's the comment that Phil had made that I copied and pasted on the slides. Heuristic approximations are fast and hence particularly useful. The fraction of objects that get detected is a number that is normalized naturally between 0 and 1, and therefore it's obvious to understand what the performance is for when you compare the opsims. But it really doesn't matter so much because the way you want to use it is comparatively. So if you have a goal and you come up with a metric that is a single number, and you have a description of an opsin that gets implemented, so that's your bench line, and everything else can be evaluated in, as a comparison to that. And then again, weighted by the importance of the science case.
Okay, I have two very general curiosities, and probably they are not directly related to your talk, so I apologize for that.
No, that's totally fine.
The first one is when you speak about running, our code on an LSST machine, you mean the catalogs or the images?
Right, actually I wanted to go and show you some of these. So sorry if some of you have already done this, and so that's going to be boring, even more than it was the first time. Sorry about that. But so this is a list of opsins that have been run. This particular list, I think, is the most recent list, and I think they've been run with the new implementation of the opsin simulator, which is more accurate and more like actually the sky will decide what to observe. Those details matter only up to a point. Here is a list of already implemented simulations, so potential LSST surveys that have been designed and simulated. And you have a small description here. I just asked Lynn and Peter if there is a longer, more detailed description somewhere to each one of these. Basically, let me get a couple of steps back. What the opsim is an SQL database that contains information about what was observed when and what is the quality, the image quality. Depending on the requirements that you put into the opsim, I need this opsim to run 3 images every night on the same field into filters, as well as simulations of weather, patterns, and some randomness, etc., etc. So that's this object right here. If I click on it on this GZ file, it's really big because it's the database for 10 years. And then against that, you can run your metrics, and you get things like this. No, that's not what I wanted to do.
Sorry. I think the question was about processing the images after they were taken.
Oh, processing the images after they were taken. Sorry. But I'll go back to this afterwards. So actually, let me just finish this, and then I'll try to punt the question to Colin, because I probably can't answer it. So then you have a metric, say one of those that have already been created, the maximum air mass, and then you produce this plot. If your metric that measures your figure of merit on a scale from 0 to maximum happiness is available, then every opsin run that gets created can have a plot like this and a histogram like that, etc. Do you want to repeat your question to me?
Okay. The second is a more general curiosity about the strategy. I was wondering, with the 2 snaps, if you lose a lot of solar system objects, the nearest one, for example, the main belt objects and some important families as the Trojans, because no doubt that if you observe the sky every 3 days, you get the trans-Neptunian objects.
Right.
But to have a sure detection for a nearby object, for example, in the main belt, you need 3 observations. And so I was wondering if it's better to adopt 3 snaps instead of 2.
You mean 3 images, not 3 snaps? 3
snaps.
Too close.
Yeah.
Too close for even from my understanding, too close in time.
It's not my business, so...
Right. No, I'm going to bring up, so this is, by the way, the thread in which I open on community to discuss the pros and cons of moving away from the 2 snaps, and I encourage you all to look at it and contribute to it. This may turn into a white paper. Megan Schwab is the co-chair of the Solar System Collaboration, and her statement here is very clear. Pretty much anything less than getting a sum of 30 seconds on sky per visit will significantly impact solar system science. So the motion, even of the fastest thing, is not such that a shorter exposure would affect it. that would affect the image on the sky in terms of moving too fast, but they're worried about detecting things that are faint that cannot be detected by other surveys. So they want a co-added depth of 30 seconds. And because if you do it in a single exposure, you gain 7% of the survey back, so they can sneak in a north ecliptic spur survey or something like that. They favor that.
Okay, it's basically what my question. Thank you.
Colin, do you want to answer the first question that I didn't get?
I guess I'll do this in reverse order because I want to add a little bit more information about snaps also. Just context of why this is such a discussion recently is that part of it is that in the original design, the snaps were designed to do cosmic ray rejection. That was why back in the early 2000s it was thought that this was a great idea, is then you can then identify things that are different between the two snaps and say, oh, well, that's a cosmic ray. It couldn't have been an astrophysical object. Let's throw it out. We no longer think we need that. Basically because with thick CCDs, the tracks of cosmic rays now look so different than they used to in the thin CCD era that we believe we can morphologically reject these quite effectively. So it's not even in our nominal plan that we will use the snaps for cosmic ray rejection. So that's kind of one of the drivers that's not so much of an issue anymore. Another thing, and I think this is subdominant compared to the 7% gain in efficiency, is that in a handful of the sensors delivered to the project, there is a little more read noise than we like. It's something that's not worrying. We still meet all of our requirements on the survey itself, but it's enough that it makes us consider if we bump up the time it takes to read out the sensors. So if we go from a 2-second readout to a 2.5-second readout or a 3-second readout, that's a huge gain in read noise. So you really drop the read noise floor way, way low. And so, I mean, the read noise levels that we're talking about are still not dominant compared to the sky background noise in everything except U. U is always a kind of scary band, which is why we don't plan on doing snaps in U. So it gives us a little bit more margin on the overall noise threshold, and it's something that we've sort of only seen in the past 6 months or a year or so. So that's why there's a little bit more of this coming out now than there was discussion sort of a year or two ago. So does that make sense? Okay. Second, on your question of image of processing the special programs data, we fully will technically support the ability to reprocess images. So you'll have all the same data management software available. There's a batch system that's designed to be attached in the same data center, so you'll be able to access all the images through that mechanism. So technically, it's totally possible. You don't have to just live with the images as catalogs as we create. However, we say 10% of compute goes to the users for whatever they want to do. That's not actually as much as you might think. That's not quite enough to say, oh, I'm going to reprocess another 1,000 images or so. Well, I mean, right, so at some point we're going to have to make actual decisions about how we allocate resources like this. So we're going to be providing Jupyter notebooks to everybody. How do we trade off letting somebody reprocess 10,000 images versus letting a whole lot of users do their own ad hoc analysis on the catalogs themselves? I think you should kind of expect that if you're thinking about a significant reprocessing campaign, that might require resources above and beyond what we're providing.
Correct me if I'm wrong, but I think that the reason why statements that are more clear about how many users and what kind of access will each user have, etc., have not been made yet is because it's far enough in the future that computational resources may change somewhat from what is available right now, right?
Completely. It's a lot of these are kind of in a dry, formal sense. These are decisions to be made by the operations team when the telescope is in use, and it's actually not the job of the construction team right now to define all these questions in great detail. So it'll be clear once we have the hardware sitting in the data center, and it's just hard to predict right now.
One other thing about the snaps that I don't think we mentioned, the snap strategy doesn't have to be homogeneous for all the surveys or for all the sky. So if you're really interested in in between the 30 seconds variability, maybe we can propose for like 4 snaps that sum up to 30 seconds for some crazy region of the sky for some small amount of time. So even if we move to a 30 seconds overall, that doesn't have to mean that we moved to over seconds overall for the entire sky and for all the surveys.
Right. Technically, we will preserve the ability to do this. We're not trying to descope it and forget how we build snaps together into single visits. We will preserve this ability, so if you really just want to say, oh, I want 10% of the R-band images to have this property or this particular region of the sky, we will support that.
Thank you. On the template,
Yes.
actually the section of performance evaluation, I'm reading the call, and you also highlighted something like this. In the call there is written that this section must contain methods to evaluate the effectiveness of the service strategy modifications that we are proposing.
Yes,
And
this is the
then-
tolerance.
Yeah, and then say in light of potential effect of changes proposed in other white papers.
Right.
What does it mean exactly?
So this is what I mentioned earlier here, that it's not exactly just that the SAC will rank, the idea is not just that the SAC will provide a ranked list of the white papers and then the OPSIM will be simulated verbatim as described in that particular white paper. Rather, they should design an OPSIM that fulfills the scientific goals of a white paper that is highly ranked, but possibly also fulfills goals of other white papers. So in this process of merging the papers, then they will actually design the details of the OPSIM.
So it's not something that is requested for the single white paper. I mean, as far as this is, the section must contain this in light of the other white papers.
No.
We cannot, of course, overview all the white papers.
No.
Okay.
I think if I may interpret, fair enough. If I can interpret what Gilles commented in that statement, I think what he meant is you need to provide us enough information about how to perform how to evaluate the performance of an OPSIM on your science case, which means, again, the figure of merit and the metric and the tolerance around the metric, such that we can, in light of the other submission, come up with an optimal strategy.
Because we
again,
were thinking about collaboration and trying to merge in a stronger case, similar cadences. So
Right.
I was thinking about that, like as a part of this process, we can help in advance doing this. Yeah.
Good point, yes. I think what that would end up looking like, you would have a set of performance indicators for all of the science cases, because maybe you can merge blazars and supernovae, but maybe if you come to the middle from 2 different directions, then you can't go in one or the other direction and save both sciences. So in that case, I think you would have a performance metric, for a performance evaluation sentence for blazars and a performance evaluation sentence for supernovae that would be separate.
And a more specific question about submitting white papers for collaboration among different science collaborations.
Right.
TVS is proposing a referee for white papers.
Yes.
For my specific case of young stars, we want to explore both variability and galactic plane with a deeper observation. So this could be different white papers, maybe, and in that case, it makes sense to submit to TVS and to Milky Way, let's say. What if we, at the end, merge?
So as far as I know, only TVS has a review of individual papers, Whereas Solar System and whereas Desk has merged all the papers into a single submissions, and Solar System is yeah, I know. Solar System is trying to it's going to be just like the roadmap, which is like 230 pages. And whereas Solar System is sort of trying to minimize the papers and send as much as possible a coordinated message, but not not a die-hard coordinated message like Desk. In terms of publication policy then, which is something that we also were talking about, but I think we ran out of time. But so TVS has now a drafted publication policy. Desk has a very strict, not at all drafted, written in stone publication policy. And TVS and Desk have come up with a joint publication policy for the plastic challenge, which is the Kaggle challenge on classification of transients from light curves, which was just issued 2 weeks ago. So the reason why I'm bringing it up is because of the following. If you intend to communicate with Desk and try to get anybody from Desk together to write the paper with you or to get your science case in their paper, that is a very complicated process because their review process is incredibly complex. And I think their internal submission was like last month. Other than that, I don't think anybody's micromanaging the project, micromanaging the white papers. So collaborating with any other science collaboration is fine. If you want to publish the papers as actually refereed publications, and you're within TVS, I really, really, really hope that we will have converged on the publication policy before November 30th. If you then want to turn it into an actual peer review publication or a research note or whatever, then you will have to fulfill the requirements of TVS publication policy because this is, which are designed to, protect collaboration and make sure that nobody essentially gets screwed and gives great idea out and in a conference call in TVS and then somebody else goes write them up and they've lost a good asset which they were intellectually owning. So it's not a too strict a publication policy, but it's designed to protect this. And so at that point, once we have converged on the publication policy, we'll discuss this. But yes, other than that, all the science collaborations have, for now, can collaborate fairly freely and yes, and without too many complications. And I don't think anybody else has an internal review process. Yes.
I have a naive question. Will be the SAC...
A live question or a naive question?
Naive.
Okay. Terrifying.
Will be the SAC somehow informed or even educated about a number of technicalities about feasibility and implementation of the survey, because this could be influencing,
Absolutely,
could influence
yes.
the ranking.
So this, I think LSST has a really great SAC whose advices listen to closely, but not even closely enough. And many of them have been there for a long time, and they are part of the science collaborations in some cases. They've seen the birth of LSST. Michael Strauss is excellent and is incredibly knowledgeable about everything about LSST. So they already have a lot of that knowledge in the house, and they will be definitely supported by the project to understand all the technical constraints and the technical issues that may arise. And in addition, once they have ranked the papers based on their understanding and their appreciation of the science case and the feasibility, they will work with the project to merge the OPSIMs into a reasonable number of ranked OPSIMs for implementation. So they will work closely with Lynn, John, Santiago, I think, and Peter, who's back on simulations. Any other questions?
If you want to follow the naive question, there is also one about the publication policy that came to me just for some experience that we had. Suppose that target of opportunity is going on, and then you cover a LIGO Virgo sky map, then possibly and probably LSST will find the deepest counterpart. Deep, I mean, because you go to 24 magnitude deep, so when they will be able to go deeper with the interferometer in sensitivity, then the distance will go up, and also the faintness of the counterpart will go to 21, 23, 24, depends on the distance, but anyway, the probability that LSST will play a strong role is obvious. So then this means that this result will be distributed for spectroscopy, for example, to everybody in the world, let's say.
Yeah.
So this means that so what is the publication policy in such a case? You will have this big 3,500 author paper, or it's difficult. I don't know if you think about it, but
question that I fear,
it could be.
That I fear all the time. So I think this is actually more of a question of data rights than a question of publication policy, in the sense that LSST, I don't think they intend to manage publications in that sense, but they do manage distribution and access to data. And all of the alert data is actually entirely public. So anybody can access it, anybody can share it, not really anybody can access it. Very important difference, but it can be shared with all of your friends that have telescope time, precisely because we want to enable as much follow-up as possible. So if you restrict that to the community that has acquired data rights, then you actually cut out people that potentially can produce data that are insightful about a phenomenon. Said that, what that means is that, you know, once something is discovered, it's public domain, and anybody can write about it. I don't know that there is anything that LSST can do. Yeah, so it's going to be competitive. Colin, have I missed anything about the data rights that covers this?
I think it anyway is a wonderful.
Yeah, it's a great problem to have.
You have a good return for all the LST experiment, no?
Right.
If you discover something, you are anyway the right on this. So
of course.
Just this is a good return anyway.
And it's not true that the follow-up data is public, right? So if you set up your follow-up with your close friends and they don't want to share the spectroscopy or whatever with anybody else, then your publication is based on LSST and that data, and it's uniquely accessible to you and your team. So you can actually still protect the follow-up data, but in that sense, LSST is truly an open source.
Anyway, even LSST can play a role in the follow-up. If it's decided that's possible, they can follow the source, go down, and then
right. So that
change the things again, but it's open.
Right, actually no. Let me take all that back, because the alert is public, but it's not clear what TO, it's not defined what TO would look like for LSST.
Yeah.
So the alert is public.
I was thinking about this, and this is an extremely high-level question that I do not take this as like 5 sigma definitive.
It will not be me and Colin making this decision, that is for sure.
But the way I understand it, I don't think we can do follow-up of TOOs that are not themselves public. Like we can't keep it secret, observe some area and not tell people why we're observing that area, and then just wait for the LIGO folks to go pick out the interesting bit from the data. So my assumption here is that TOOs will be public, that they are TOOs, and that this is the region that we're going for, because just for transparency reasons, and just because we can't give away the telescope time in that fashion. It has to go to the telescope time, and the utility of the telescope has to go to the entire US, Chilean, and international community.
And so I assume that the way, I mean, obviously, again, this is not really defined, but I assume that the data products that you've described would extend to all TOs. So when you go on a particular area of the sky to detect the gravitational waves counterpart, then all of the alerts in that area of the sky have to be made public because they're still part of the alert packet, part of the prompt data release.
I don't think we change our processing any for TOOs. I think it just changes the scheduling.
Right.
We can point anywhere in something like 90 seconds.
Right. This is a slew.
Yeah, so it's... Yeah, we can get on target faster than people will be able to get targets to us, right? It'll take some amount of vetting and just Lego processing.
The speed of the LST is terrific, so you can point much as quick as satellite, really. So that's incredibly competitive also for different wavelengths and so on. So having in-ground this kind of facility is really a step over because we don't know what's happened in the optical after half an hour or so. If LIGO Virgo will give us alert within 30 minutes or so from the arrival of the gravitational wave, this is a science that we don't know. It just with one pointing of LSD, one, say, 10.
A few.
One tiny little follow-up on that is that, just because it's kind of interesting, what do I want to say? We will publish the next 10 or so planned visits ahead of time, so you always know where we think we're going to go, but at any time we can scrap that list if a TOO comes in and we'll just say, okay, that's all canceled, we're now going to this, this, and this. And that's something that we expect to happen semi-regularly. Clouds move in, cancel those visits that were planned, let's do something different.
I didn't know that. So 10 visits is the set?
It's something like 10, it's like, I forget how it's formally defined, but it's some number.
So there's a 5 minutes lag in change of plan. That's another way to say it.
Sorry?
Except for TO, there will be a 5 minutes lag in the change of plan.
No. We will publish the plan that we think we're going to do.
Right, and so that means that the plan extends to at least 10 images.
Yes.
Because I don't think the scheduler plans the whole, it doesn't plan the whole night, right? It plans on
right. It plans a certain number of visits in the future. It will publish those. It has the option to decide that that's a very bad plan and change it, but it at least gives you some idea of where we're going in the sky.
So even within the 5 minutes, the 10 images, you can still change that even if it's not TO.
I believe so, but I don't remember the exact criterion. Just the other tiny note is that slew times are limited by the dome. If you need to move from like the east side of the sky to the west side of the sky, the dome actually moves slower than the azimuth axis of the telescope. It's a big, expensive thing to spin. Yep. Right. But we're definitely
so this may
happen
it may still happen in the context of mini surveys. And then there has to be a decision about a rule to interrupt the mini survey, which will be probably different from a decision to interrupt the wide fast deep. But those decisions depend on what mini surveys you have and what the constraints are on that.
Once again, I have a curiosity to come back once again to more technical issues. You talked about image quality, but image quality is something that is a weird definition, because typically you are thinking about mainly to air mass.
Air mass and darkness, I guess.
And?
And how dark the sky is.
Yeah, but the point is that on top of this, moon, no moon, there is also seeing constraints.
Yes, you can
Is
also...
the-
Go
Yeah,
ahead.
so we have to think about also what kind of seeing distribution we would like to have for the measurements that we are interested in.
Yeah.
Because obviously, if I remember correctly, someone showed us that the Maribel, it was 1.5 arc seconds of the seeing at the top of the distribution that you are thinking
Yeah.
about, or what?
This is, I don't know which simulation this is, so I don't know if it's at the high end or the low end of the seeing quality, this is baseline. And so this is, I don't know what F stands for, but I
wait a
assume
minute.
that this is...
This is pretty horrible. It cannot be like that. You are in Chile.
Isn't it?
Come on. This is the Palermo seeing.
No, what is that? Does anybody know what it is? Ah, sorry. This is the distribution of maximum seeing. This is the distribution of
Maximum seeing.
yes.
Okay.
We can do
Yeah,
the
not the
median
mean
seeing.
seeing. Okay.
What band would you like?
Okay. No. Okay. Now these numbers are more plausible. Okay. This is something that we really need this kind of information.
Yeah.
Because
so this is automatically run on all the options.
Yeah, because otherwise we cannot, for example, concerning the air mass, there is no doubt that for those ones that are interested in using ZY, this is less severe. Even the twilight is less severe. So it's something that we can specify in the white paper, but we need to have these numbers to have at least an idea of the fraction of the time in which the seeing is going to be better than.
Yes. So, and your science,
So this is
your figure of merit could be entirely
it
related
depends.
to this.
It depends on this kind of distribution. Okay, now I feel it.
I think it's also very important when you provide distribution of seeing, median seeing or whatever, also providing timescales, because very often, I mean, if you look at the median seeing of many observing sites, they are very similar. The problem is for how long you get a given seeing within the night, within 3 hours, normally the median seeing is average over months, or I think
So
it's
this
also very
is-
important to have the time scale.
This is for the entire survey.
Yeah.
So let me go back to...
So these are distribution within an exposure?
No, so
No.
generally...
I don't understand
Yeah,
your
so
point.
these
That's why I was asking.
I'm going to make an assumption, and I'm going to assume that this is the scene per exposure.
Per exposure,
over
okay.
the entire 10 year of the survey.
Okay.
So, but a metric exists for calculating, for giving you back the seeing. And so if you think about the video, then it's just an SQL constraint to say, tell me what the seeing is in chunks of a day, and then pull out a bunch of these plots or average over a whole bunch of these metrics. And there is a specific tool for aggregating statistics. So if you get the median seen per night, then you can have the median of the median seen per night or whatever you want.
Okay.
Is that just the median seen? No, it's not. The mean will be
Just
the mean seen.
one word of caution that you should ask the OPSIM pupil what seeing model they put in before doing that experiment, because I'm not actually sure if it includes, what it includes in terms of a time-dependent structure function. And so whatever you get is just going to be whatever they put in, so.
But it must,
it's-
because it has simulations of weather.
Sorry?
So it has simulations of weather, right?
Right, so there's some function.
But what is the time scale at which the weather changes?
Yeah, and so you can probably just ask them faster than you can recompute it, and it'll. Right. Right. It does do the right seeing for the different filter wavelengths. It does compute that assuming these. Yeah, that structure function. There's a lot of structure functions.
I'm trying to get the answer.
People have woken up now in the U.S., so.
Lynn is up, she's answering my questions already. We'll see. I will take other questions in the meantime. Right, brought to you by Slack. I will report back if she answers. We don't have to stare, because a stare Slack never answers. That was funny. Tough crowd. That was a funny joke, man.
Okay, if there are no other comments, questions, maybe we can end here with the session. Thank you all the speakers of today. Many thanks for